It is exactly 4 o'clock in the morning, somewhere in the vast, dark expanse of the South China Sea. Inside the high-security combat direction center of the world's most expensive warship, the air is thick with a silent, electric tension. Suddenly, a series of unidentified blips flicker across the state-of-the-art radar screens. This isn't a drill. How do you even begin to destroy a target like this? We are talking about the USS Gerald R. Ford, a 1,100-foot-long floating fortress, a $13 billion masterpiece of American engineering. For decades, the Pentagon and the Indo-Pacific Command have operated under a single, terrifyingly confident assumption: this ship is unsinkable. Utilizing a massive network of Aegis Combat Systems, silent nuclear reactors, and over 4,500 highly trained personnel, the Navy believes they have created the ultimate deterrent. But what if that assumption is wrong? What if an entire nation decided to throw every single missile, every drone, and every submarine in its arsenal at this one specific point on the map? Could the pride of the US Navy actually survive a total coordinated onslaught? Or are we looking at the most expensive graveyard in maritime history? To understand the answer, we have to look past the massive steel hull. We have to dive deep into the classified layers of defense that make the Ford a ghost to some and a god to others. It is an unprecedented architecture of security, a web of sensors and firepower designed to stop a war before it even starts. But even gods have a weakness. This is the anatomy of the ultimate phalanx. This is why the world's most dangerous ship might just be immortal. But pulling off a strike isn't that simple. In the first wave, you aren't just facing a ship, you're facing a literal fortress of iron. To even get close, you have to bypass a structure 25 decks deep. It's constructed with HSLA 115 high-strength steel material so resilient it requires specialized plasma arc welding just to bond the plates. This isn't just a hull. It's a shock-hardened shell designed to absorb the kinetic energy of a near miss from a tactical nuclear weapon. Deep in the belly of this beast, the power is absolute. Two A1B nuclear reactors churn out 250% more electrical capacity than any carrier in history. This isn't just for propulsion. This energy fuels a massive grid of high-energy sensors and future-proof laser weapons. It allows the Ford to operate at peak lethality for 20 years without ever needing to refuel. It is, for all intents and purposes, a self-sustaining island of American power. But here's the critical part. You aren't just fighting the Ford. You are fighting an entire ecosystem of calculated destruction known as the Carrier Strike Group. Surrounding the carrier is an armada of Arleigh Burke-class destroyers and Ticonderoga-class cruisers. They function as the ship's personal bodyguards, forming a multi-layered shield of steel and silicon. They are the outer air battle defenders, and their mission is simple. Nothing reaches the carrier. At the heart of this defense lies the Aegis Combat System. This is the brain. It is a sophisticated web of AN/SPY-6 active electronically scanned array radars. These sensors are 30 times more sensitive than previous models, allowing the fleet to see objects the size of a bird from hundreds of miles away. Aegis doesn't just detect you, it tracks you. It can manage over 100 targets simultaneously, from sea-skimming cruise missiles to high-altitude ballistic threats, calculating intercept trajectories in microseconds. Before you even clear your hangar, the system has already assigned a weapon to your tail. It feels like an impenetrable wall, a fortress so technologically advanced that no missile should ever be able to touch the paint. It is a masterpiece of impossibility. But in the world of high-stakes warfare, even the most perfect system has a breaking point, because as every engineer knows, the more complex the machine, the more devastating a single tiny error can become. And that brings us to the moment the math starts to fail. But even the most perfect defense has a shadow, a limit that isn't defined by the thickness of the steel or the heat of the reactors, but by something much more cold and unforgiving: math. In the world of high-end naval warfare, there is a term that keeps admirals awake at night: mathematical saturation. Think about it. The Aegis system is arguably the finest computer brain ever built for the purpose of destruction. It is fast. It is precise. It is relentless. But even the fastest processor in the world has a clock speed. Every radar array has a finite number of beams it can generate at any given microsecond. Even the most advanced AI has a limit to how many unique, high-velocity objects it can track, identify, and assign a firing solution to before the buffers begin to overflow. This is the KO, the fatal flaw in the logic of absolute security. If you can't bypass the shield, you simply try to break the machine that holds it. Imagine a nightmare scenario in the Pacific. A coordinated, multi-domain swarm designed specifically to push the Ford's computers to the point of total cognitive collapse. We aren't talking about a few dozen missiles. We are talking about a barrage of over 100 incoming threats, all converging on a single coordinate in the exact same second. The attack starts from the sky. Hundreds of low-cost, low-altitude suicide drones clutter the radar screens, creating a cloud of digital noise that forces the system to waste precious processing power. While the computers are busy sorting through the trash, the real killers emerge. From the horizon, sea-skimming cruise missiles scream in at Mach 3, staying just feet above the waves to hide in the curvature of the Earth. Simultaneously, from the upper atmosphere, hypersonic glide vehicles perform unpredictable maneuvers, falling at 5 times the speed of sound. And from the depths, silent attack submarines launch a spread of heavy torpedoes to overwhelm the acoustic arrays. It is a digital avalanche. Inside the Ford's Combat Direction Center, the air turns cold as the screens saturate with red icons. The Aegis system begins to prioritize. It calculates intercept trajectories, it assigns missiles, it attempts to jam frequencies, but the clock is ticking. In this split second, the machine is fighting a war of numbers. It's a race against the laws of probability. If the system fails to prioritize correctly by even a fraction of a percent, if it misses just one lethal target buried inside the swarm, the entire $13 billion investment is gone in a flash of light. So, how do you stop a storm that was engineered to be unstoppable? The answer isn't just in the computers. It's in the raw mechanical violence of the weapons themselves. Let's look at exactly what happens when the math stops and the metal takes over. When the math begins to fail and the sensors saturate, the USS Gerald R Ford stops being a passive observer and transforms into an apex predator. This is the point defense phase, the moment where the ship's survival depends on pure, unadulterated mechanical violence. The first line of this inner sanctum is a weapon system, so iconic it has become a legend in naval circles. The Phalanx Close-In Weapon System, or CIWS. To the uninitiated, it looks like a tall white dome, often nicknamed R2-D2 with a bad attitude. But look closer. Beneath that red dome is a 20mm M61A1 Vulcan Gatling gun, a beast of engineering capable of a staggering rate of fire. 4,500 rounds per minute. Let's break that number down. That is 75 rounds every single second. At this speed, you don't hear individual shots, you hear a low, terrifying growl that sounds like the very fabric of space is being torn apart. But the real magic isn't just the speed, it's the munitions. The Phalanx fires armor-piercing sabot rounds made of tungsten. Tungsten is 1.7 times denser than lead and nearly as hard as diamond. When a multi-million-dollar anti-ship missile is screaming toward the hull at Mach 2, it possesses immense kinetic energy. A normal bullet would just bounce off. A tungsten sabot, however, punches through the missile's airframe like it's made of wet paper, detonating the warhead or shredding the guidance fins. The CIWS uses a closed-loop radar system, meaning it tracks both the incoming target and its own stream of tracer fire simultaneously, adjusting the aim in real time until the two tracks merge and the target is obliterated into a cloud of harmless confetti. Moving slightly further out, we encounter the CRAM and the RIM-62 Evolved Sea Sparrow Missile, or ESSM. This is where the engineering enters the realm of the impossible. The ESSM is a medium-range surface-to-air missile designed specifically to counter high-speed, highly maneuverable anti-ship cruise missiles. To do this, it needs a level of agility that defies human biology. The missile is powered by a solid-fuel rocket motor utilizing a sophisticated high-energy propellant. This mixture is engineered for an extreme thrust-to-weight ratio, generating massive chamber pressures in a fraction of a second. This allows the ESSM to perform high-G maneuvers up to 50 Gs. That means it can turn tighter and faster than any manned aircraft or incoming missile on the planet. A human pilot would be turned into jelly at those forces. But the ESSM just keeps turning. The brain of the ESSM uses a dual-mode seeker that combines radar homing with an inertial guidance system. It doesn't just chase the target, it uses predictive algorithms to calculate the most efficient intercept point. It is essentially solving a high-velocity calculus problem in the middle of a hurricane. The vertical launch system on the Ford can ripple-fire these interceptors with millisecond precision. The reaction time is almost instantaneous, from the moment the AN/SPY-6 radar identifies a lethal threat to the moment the vertical launch hatches blow open. Less time has passed than it takes you to blink. The automated loading systems are a marvel of mechanical engineering, cycling munitions with zero human intervention. It is a flawlessly synchronized ballet of high explosives and precision optics. This is the value of $13 billion. It's not just the steel, it's the ability to dominate the physics of a split-second encounter. But how does all this technology hold up when the pressure is real? To truly understand the Ford's survivability, we have to look at how these systems work in harmony across 3 distinct, high-stakes scenarios. This is where the strike group proves its worth. Scenario 1. The long-distance kill. Imagine an enemy strike group or a land-based battery launches a barrage of long-range anti-ship missiles from over 300 kilometers away. The Ford doesn't wait for them to get close. This is the job of the SM-6, the Navy's premier long-range interceptor. The SM-6 is a masterpiece of multi-mission capability. It can climb into the near vacuum of the upper atmosphere using its active seeker head to hunt down its prey. In this scenario, the forward acts as the eyes, sending data to a destroyer miles away, which Sawdahl launches the SM-6. The missile intercepts the threat 240 kilometers out, long before the carrier crew can even see a flash on the horizon. It is a clean, surgical removal of the threat. Scenario 2. The layered saturation. What happens if the enemy launches a swarm of 50 missiles simultaneously? This is where the saturation logic we mentioned earlier comes into play. If the long-range interceptors can't get them all, the defense drops into the inner tier. Now it's a battle of numbers. The Aegis system on the forward and its escort ships begins a process called launch on remote. The computers are calculating lethality in real time, which missile is the closest, which is the fastest, which one is aimed at the carrier's bridge. The ESSM batteries and the CRAM systems fire in a coordinated rhythm, creating a kill zone roughly 15 to 30 kilometers from the hull. This is high stress, high-frequency warfare. The automated systems are cycling at peak capacity, and the sky is filled with the smoke of dozens of simultaneous interceptions. It is the ultimate test of the system's cognitive buffer. And Koi Kung, we have Scenario 3, the invisible war. Sometimes the most effective way to destroy a target is to make it lose its mind. This is electronic warfare. Imagine a modern, infrared-guided missile has bypassed the physical interceptors and is just seconds from impact. The forward doesn't panic. It activates the SLQ-32V7, a massive suite of high-powered jammer arrays. The system bombards the missile's seeker with a wall of electromagnetic noise, making it impossible for the missile to distinguish the ship from the background of the ocean. Simultaneously, the ship launches Nulka decoys, active hovering rockets that mimic the radar signature of a giant aircraft carrier. The enemy missile, suddenly seeing two forwards on its sensors, chooses the wrong one. It turns sharply, chasing a ghost into the waves while the real carrier remains untouched. This isn't just luck, it's the satisfaction of outsmarting the enemy's logic. It is the final invisible line of defense that makes the USS Gerald R forward the most difficult target on the face of the Earth. But even with all this power, there is one thing that even $13 billion cannot buy: perfection. Because in the world of high-tech warfare, the biggest threat to a machine often isn't another machine. It is a single, overlooked human detail. It's a bitter irony. $13 billion, 100,000 tons of shock-hardened steel. But every single pound of that power is held together by something remarkably fragile, a process, and processes are run by humans. In the high-stakes world of modern warfare, the butterfly effect isn't just a theory, it's a nightmare. Imagine this. A single maintenance technician skips a routine sensor check on the electromagnetic aircraft launch system. The EMALS, this $800 million system, is the heart of the ship's offensive power. If a single magnetic coil misfires because of a microfracture or a software glitch in those 8 million lines of code, the jets don't launch. The long-range shield vanishes. The fortress becomes a sitting duck. Or even more humiliating, while the Aegis system is busy scanning the horizon for Mach 5 missiles, a commercial drone, costing less than a cheap smartphone, slowly drifts over the flight deck. It doesn't need to sink the ship. It only needs to carry a pound of high explosives into the delicate arrays of the dual-band radar. If the eyes are gouged out, the giant goes blind. It's the ultimate paradox. The more complex the machine, the more ways it can break. True strength doesn't lie in the thickness of the hull. It lies in the terrifying perfection of the people who operate it. Because in the end, $13 billion algorithm is only as strong as its weakest human link. The US Navy didn't just build a ship with the USS Gerald R forward. They built a security algorithm made of iron and fire. It is a masterpiece of engineering designed to solve the most violent equations on Earth. But as we've seen, the battle for the ocean is never truly won. It's just managed, second by second, by the machines and the men who dare to sail them. We are just getting started with our deep dive into the world's most lethal technology. In our next video, we're heading beneath the waves to explore the silent, nuclear-powered ghosts of the deep, the Virginia-class attack submarines. Or maybe it's time to look at the sea, air, and land components of the nuclear triad. You won't want to miss the technical breakdown of the weapons that keep the world on edge. Subscribe now, and we'll see you in the next one.